And welcome fellow solar people. Today we're going to be talking water pumping with photovoltaics, and I'll be discussing water pumping with direct solar, not systems with batteries or other energy storage, which is just more like a normal load, so we won't really go into that today. But we'll just talk about direct pumping with PV. To do direct pumping, there's several points to understand. For one thing, direct water pumps don't need batteries or separate inverters. It's just PV direct to a motor running a pump, essentially. Batteries can be used to extend pumping times during the solar day if necessary. If there's not enough water pumped during a solar day, you might be able to store energy in a battery and pump for longer hours. Pumps are available anywhere from 12-volt nominal to 400-volt plus systems for larger systems, and it varies by the pump model. Excuse me. Pumps are available for most water sources and applications. It could be drilled or dug wells, ponds or lakes, streams and rivers, and used for a variety of uses, such as household water, irrigation, water transfer, livestock, fountains, swimming pools, many other uses. Some pumps do require filtration. Others work with dirtier water. So depending on what your water source is, you have to choose the right pump for that. And using PV direct pumps to fill storage tanks or cisterns is generally how it's done. PV pumps run at variable speeds during the day depending on the strength of the sunlight and the time of day. So it's not like you get a consistent outflow from pumps that are run directly off solar panels as you would off a more stable energy source. So generally they're used to fill tanks and cisterns rather than for direct application, although there are instances where direct application could certainly work. Used a lot for homes, businesses, or farms. Again, generally used to fill non-pressurized storage tanks or cisterns because, again, since the power source is variable, you don't have a consistent flow and consistent pressure. And water is only pumped during the daytime, obviously. We don't have PV modules yet that work with moonlight. Performance is measured in average gallons per day. Most pumping applications and people that are familiar with pumps rate pumps in the gallons per minute range, but because of the variable nature of solar, what we're really looking at is a total accumulation over the day. So the gallons per day is a much more important figure than the gallons per minute. The gallons per minute can still be somewhat important in terms of what your water source is. So for instance, if you have a well that produces 10 gallons a minute, you can't pump that well at 30 gallons a minute without running dry. So, we do still need to know a gallons per minute figure, but it's not real applicable to the pump itself in terms of its usefulness to you. And typically, they're used to fill storage tanks that hold several days worth of water, and that's what carries you through the cloudy weather or hazy weather or times when you pump less, because you're going to pump more water on some days than others, and to have a steady water source, you want to store that water. It's much cheaper, easier, and more efficient to store water in a tank than it is to store energy in a battery. So that's generally how that's done. And PV pumps can be used for direct irrigation as long as the irrigation can occur during the daylight hours and as long as the variable flow rate is acceptable. So storage tanks in a variety of sizes. The type of plastic tanks you see here on the right are pretty common, but you could certainly have concrete tanks or other cisterns or such, either above ground or below ground. Stock tanks, like you see on the left bottom there, is just another direct source. So when you go to design a system, there's some information you have to gather. First is the site location, so we need to know what the climate and the solar insolation data is for a particular site. We need to know what the water is going to be used for. We need to know a seasonal water pattern. Many places, particularly in the West, have a lot of water use in the summertime, but very little in the wintertime, so which fits perfectly with solar. We need to know the type of water source. Is it a well, a catchment basin, an open channel, creek or a stream? water volume is provided by the source, so we need to know what the available water is. Obviously, that's the limitation of any pumping system, is how much water is actually available. Water quality is important. We need to know if it's going to be potable water for household use, or whether it's irrigation water, whether it's clean or what we call turbid, which means it has a lot of dissolved solids in it. It might be just silt or sand or just a general turbid to it. And we need to know the total pumping head or lift, and that's the well depth or elevation difference between the source and the tank. The well depth itself is one measure, but typically in a well, the water level actually stands higher up than the bottom of the well, obviously. And really, we just need to know the elevation change from the water surface to the top of the storage tank or the top of the place where the water ends up. So what is head? There are two measures of head. One is called static head, and that's the total elevation difference between the water source and the top of the storage tank. And again, if this is a well, it's not the depth of the well, it's the actual water level in the well, and then to the top of the storage tank. And that's an elevation difference, not the length of pipe to the tank or the actual distance, it's just the elevation change. So static head can be measured using an altimeter, a GPS device, or maps, any method that you would have to do that. Now, dynamic head is that static head plus the friction losses in the pipe. Excuse me. As you're pushing water through a pipe, there's friction in the pipe, and so that amount of energy it takes to push that water through the pipe has to be accounted for. There's a number of calculators online. I have one link measured here, but there's, depending on the type of pipe you're using, there's different amounts of friction within the pipe. And it's generally done per 100 feet of pipe, and you just add up the length of pipe to get your total friction loss. So here's a diagram example of this. As you can see in what it shows is the well, that the pump is below the water level, and yet the total head is measured from the water level to the top of the storage tank. And then we do need to know the pipe length and size and type of pipe so we can figure out the friction losses. Here's a typical chart here. Again, water flowing along the inside surface of a pipe generates friction, represents a power loss that must be overcome by the pump. Friction loss increases with flow rate and length, but decreases with pipe diameter. So if you have a very long distance or a lot of water to pump, you'll need a larger pipe. And you can see from a chart here, for instance, if you look at the chart, it's a 10 gallons a minute. You wouldn't want to use a 3/4 inch pipe because you have 10 feet of head loss per 100 feet of pipe. That's enormous. You generally want to keep your head loss really, down as low as you can. That's economical for the pipe. But in this particular case, at 10 gallons a minute, I would aim at least 1.5 inch pipe, which is giving you less than 1 foot of head loss per 100 feet of pipe. In this case, it's 0.72 on this chart. So there's a relationship between head and pressure. It's just another way to measure the actual lift of the water. So head in feet divided by 2.31 equals the pressure in pounds. Or if you have the pressure in pounds, you can multiply by 2.31 to get the head. So for instance, 100 pounds of pressure times 2.31 would be equal to 231 feet of pumping head. Or similarly, if you had 231 feet of pumping head and you divide it by 2.31, it would equal 100 pounds of pressure. So be sure to use the same units when adding static and dynamic pressure components. Obviously, you can also convert this into metric measures if you need to. So one thing about pumps is that pumps can push water fairly simple. It's just a function of the pumping power. However, pulling water is a whole different function, and it's really based on atmospheric pressure. The theoretical limit of being able to suck water up from a source is 33.9 feet, but as we know from reality, theory and reality don't usually match. So for most pumps, really they're limited to no more than 20 feet, and many pumps even less ability to suck water up. So you want to get your pump as vertically close to the water surface as possible. Obviously, a submersible pump doesn't have this issue since it's always submerged in water. A pump that might be next to a above-ground storage tank, for instance, would also be essentially what we call flooded inlet, or be essentially in the water. It wouldn't really have any suction capacity. So there are many types of PV direct water pumps, and in this field we use many more types of pumps than you generally see in the normal pumping world, mostly because the power source is more variable, generally of lower power, and so we want to look for the most efficient type of pumps to do a particular job. So there's lots of variety in solar pumps. Surface pumps, again, pumps can be located no more than 20 feet above the water surface, and actually you have to subtract 1 foot to that for every 1,000 feet above sea level due to the change in air pressure. So they're often used in very shallow wells, or from ponds and streams, or spring boxes, or from tank-to-tank pumping. Submersible pumps are installed below the water level, usually in a well, although it could be in a tank or cistern, with an outlet pipe that extends to the surface or higher up a hill. It can pump surface water with some special design considerations. Most submersible pumps can be laid flat, for instance, in a cistern, and I'll talk about that a little bit more. Jack pumps are used for very deep wells. If you're not familiar with jack pumps, they're similar to what's used in oil fields, where you have a reciprocating arm that's essentially pulling a piston pump that's deep in the well. Unfortunately, there aren't any commercial manufacturers of solar-powered jack pumps right now. You can get jack pumps and you can convert them yourself, but there are no actual pre-made kits, unfortunately. There used to be, but there just hasn't been a huge market for that. And then there are circulator pumps, is another type of DC PV direct pump, often used in hot water systems, for instance, and they're just designed to move water around in a closed system, such as hydronic heating, or a swimming pool would be a similar application. So I'm going to go through some of the different pump designs here. Centrifugal pumps are probably the most common type of pump out there. They move water by spinning it through an impeller. The water enters through the middle and is spun out towards the outer edges. And I showed a couple different kinds of impellers here and a couple different kinds of centrifugal pumps. They often have very high output, but relatively low pressure. You only get small amount of pressure for each impeller, but multiple impellers can be used to increase the pressure. So, for instance, we see the cutaway of the submersible pump on the right side there. You'll notice at the top that it has 6 stages, so there's 6 impellers in there. And as water passes through the first one to the second one, it's an additive effect of pressure. So the more stages you have, the more pressure you can get, and therefore overcome more head. Centrifugal pumps generally require much higher RPMs because it's really working on a centrifugal motion. These are not what we call positive displacement pumps. And many of these models do require a linear current booster or a pump controller, although some don't. The primary function of a linear current booster is to get the pump spinning in low power conditions first thing in the morning to overcome the inertia. And before there's really enough power to actually move water, it'll at least get it spinning and you won't have a locked motor effect. Centrifugal pumps don't offer a whole lot of initial load. They often can be used without LCBs. It depends on the model. Diaphragm pumps are another method of pumping. Uses a pulsating flexible diaphragm to pump water. Generally there's a cam action on a rubber diaphragm and a set of valves, kind of similar to a piston engine or something like that. Typically can pump moderately dirty water since you essentially have a flexible diaphragm, usually made out of rubber material. You don't actually have rubbing metal parts, so it can usually handle dirtier water. They can typically run dry without damage, although since pumps are cooled by the water flowing through them, they will overheat over time, so it's not a good idea to just have it run dry for extended lengths of time. They're considered positive displacement in the sense that each fluctuation or each pulse of the diaphragm is a set amount of volume of water. So, for 1 RPM or 1 revolution of the pump, you have a certain amount of water pumped. And it can pump water at slow speeds because it's just filling up a chamber with a flexible diaphragm and then pushing that water out. So it can run at very slow speeds and still pump some water. And linear current booster is required for these type of pumps because they're essentially starting off under pressure. And so you need to be able to get that motor spinning and overcome the inertia. Another method of pumping is what's called a Rotaryvane pump. These are similar to, like Diaphragm Pumps uses their slow pump or their flow light booster pumps are done this way. It's a very interesting design. It's essentially a paddle wheel set in an offset chamber, as you can see from the diagrams here. And with every revolution, also pumps a set amount of water. So it is positive displacement. These can handle much higher pressures, heads up to over 400 feet. Can also pump at slow speeds, another advantage for solar pumps. You don't have a lot of light or early in the morning, you'll still get some water pumped, and it'll pump water over the whole course of the solar day. These pumps, however, do have rubbing parts, and they do require very clean water or fine filtration. Typically, it's recommended to filter the water down to 10 microns, which is very fine. So you do require filtration on the inlet with these type of pumps or very clean water. Another type of positive displacement pump is a piston pump, which is actually very much like an engine. It's a piston moving up and down in a cylinder and drawing in water and pushing out water. Also positive displacement. These pumps are typically very rugged and very reliable. They can be serviced with normal hand tools. They're actually fairly low tech, so they're great in many applications where there isn't a lot of access to high-tech equipment. Excuse me. So a linear current boost is also required for these because, again, they're starting under higher pressure, so you have to overcome more inertia, and an LCB will help do that. Then another type is called a helical rotor pump, also called a progressive cavity pump. This is what Grundfos uses with their SQ Flex pumps for high heads. Also considered positive displacement, although there is some flex in the fluted stator, the flexible stator, so there's some variation depending on head and pressure. These pumps can be used for much higher heads, up to 800 feet is available. And they can handle somewhat dirtier water, even though there are rubbing parts. They do handle some amount of turbidity and some amount of sand. The more sand is in there, it's going to shorten its pump life, but it will handle it pretty well. And the high lifter pump is a very unique, excuse me, actually uses the power of gravity descending through a pipeline to power the mechanism. That's a series of chambers in the pump with variable diameters and pistons in them. So it can pump a portion of the available water further uphill to a storage tank. But again, it's only pumping a portion of the water. It uses the rest of the water as its power source. These are available in either 4.5 to 1 or 9 to 1 ratios. So, for instance, with the 9 to 1, it's only going to pump 1 gallon out of 10 to go up the hill. But it can achieve fairly high heads. And because it has no additional power source, this isn't actually a solar pump, it's just a water pump, it pumps 24 hours a day. So you can actually accumulate quite a bit of water over time. You can also use multiples of these for greater water as long as you have the water source. More information in our catalog, I would certainly recommend checking that out, but a very unique pump. Useful in mountainous areas. It won't work in flat ground, of course. You have to have water that can drop downhill to the pump itself, and then the pump will pump a portion of that water further into a storage tank. So when you're doing a design, there's a bunch of things to consider. Again, we need to know what the total head, both the static and dynamic, is going to be. We need to know what the required daily water production is in gallons per day, and whether that changes seasonally. Again, you might need more water in the summer than the winter, or depending on where you are, it might be different. We need to know the size of the storage tank so we know that we can meet the required water and the tank should hold 3 or 4 times the daily requirement. It can be less if the water source is very reliable or the sun is very reliable. But generally, you want to have a backup and be able to store the water in a tank. And we need to know the recovery rate or yield of the well. Again, if a well can only produce 10 gallons a minute, you don't want to pump faster than that because you'll run out of a water source. We'll need to know what the water quality is and the location, the distance from the well to other potential power sources. It may be possible to just run the well off of, say, an off-grid home power system, and that might be more effective than actually having a set of PV modules directly on the pump. And we need to know what the solar insolation weather conditions are, whether there's any shading issues on the PV array. Obviously, if it's a forested area, your amount of sunlight available is going to be much less. So we need all that kind of information, just like what you would do for any off-grid power system, essentially. And we'll need to know what the well casing diameter is to make sure that the pump will fit down that. I get calls for wells that are only 2 inches in diameter, and there aren't any high-yield solar pumps that are going to get down there in a 2-inch opening. So typically you need at least 3-inch, although 4 to 6 inch is more common. And then we need a method of measuring the static water level in the well. There's a variety of ways to do that. Simple ways, a fishing line, a weight, and a float with a measuring tape. Obviously, you can lower the line down until the float hits the water, and then the line will go slack, and then you can mark it at that point and pull it up and measure the length. You can also use 2-conductor wire and an ohm meter, and there are commercially available measuring tools such as what's shown here. Which wouldn't really be cost effective unless you're doing a lot of pump setups, and then it might be a handy tool to have. But we do need to know where that static water level is. So here's a quick diagram of what a typical Grundfos SQ Flex submersible solar pump system would look like. If you see by the diagram, it's a fairly simple number of components. The pump obviously in the well, along with its plumbing to get the water out of the well. There's cable, of course, to go down there. And you'll need an on-off switch of some sort. It's showing number 12 here, which is an IO50 on-off switch box. And a PV array. And that's essentially all you need to have a pumping system. Is a PV array, a switch, a wire, and a pump, and some plumbing. So I'm going to go through a couple of specifics here. If you're drawing from ponds or lakes, there are some additional design considerations. Again, we still need to know what the total head is. We need to know what the required production is. And, if it's a pond or a lake, is it being refilled? Is it only a rainwater catchment that might be a set amount of water and not being replenished? We would need to know that and not drain the pond or lake completely out. So we need to know the rate of replenishment to be able to know how much we can draw out of it without reducing its water level. We need to know what the lowest water level will be compared to the pump location. For instance, if you put a pump next to a pond and it's only 5 feet above the pond, but through the course of time the pond drops 20 feet, you're going to get to the point where the pump can no longer function. You might have to move the pump down or even put the pump on a floating platform of some sort is one way to do it. But knowing that the water level may go down over time is going to be an important factor. We need to know what the water quality is, whether it's going to be potable water or whether you require filtration. One problem with ponds and lakes might be algae growth, so it might require some sort of strained suction that needs to be cleaned on occasion, so we need to know these things. Obviously, the location and the shading issues of the PV array are going to be important to determine how much power we can get. And then we need a control scheme of some sort, whether it's a float switch or a float valve or some other method of turning the pump off once the storage tank or the water delivery usage is done. You want to be able to turn that pump off. Another method is to have, if you had, say, a storage tank, You can have an overflow on that tank. That's just another pipe that goes back to the pond or lake. That's another control mechanism. However, of course, that means that your pump is running for more hours than necessary, which is going to affect its lifespan. Drawing from streams or rivers are somewhat similar to ponds and lakes, except you have flowing water. So there's a few other issues there. Has many of the same issues, but you also have to worry about whether or not, during a storm, for instance, that stream gets more raging. You don't want your pump to be washed away in a raging storm, so you have to be careful of that. Not only the inlet for the pump, but the pump itself. More likely to be sand and silt or debris clogging up the intakes. So having a very large intake screen that has a lot of surface area would be a good idea, depending on how many leaves or sticks or whatever else you find in the stream. Obviously, same location about shading and PV array location, and a controls scheme to be able to turn off the pump when your tank or cistern or other use is full. So you can also pump from tank to tank, or from a cistern, say, ground level to one up a hill or something like that. Again, we need to know what the head's going to be there. And the method of water replenishment from the lower tank that's being filled, it may be filled from a spring, for instance, or something like that, into a storage tank there, and then pump further up the hill to a second storage tank. Again, same issues of location and PV shading, and same pumping up and pumping down. Typically, when you're pumping from one tank to another, you would use two flow switches, one in the source tank that would turn the pump off when that tank becomes empty or too low, and one in the delivered tank, and that would turn off the pump when that tank is full. So they have opposite positions, but the two switches can be both wired up to control the pump. So when you're sizing a PV array for a water pump, the PV array size needs to be at least 20% greater than the rated power draw of the pump. So for instance, if you have a pump that consumes, say, 400 watts, you're going to want probably a 500 watt or larger PV array. However, you can also increase that array to get more power, or the proper amount of power for more hours in a day. So an example here, a pump that requires 1 kilowatt of power, it's 1,000 watts. You can have a 1.2 kilowatt array, would run that pump at full speed around noon for, sometime before and sometime after that noon. But the rest of the time, that array is not going to produce the full 1,000 watts. So that pump is going to run slower and not produce as much water during that time. However, if you were to use a larger array, so in this example, a 2 kilowatt array, that's going to produce 1 kilowatt of power and less light, so you're going to get more hours to go. And for most of these pumps, actually all of these pumps, there's really no limit to the size of the PV array you can put on it, other than the cost of the array itself. The reason there is that the motor in the pump is going to draw a set amount of power. Whether you have more power available or not is not going to really affect the pump. If you think about it in terms of an AC pump pumped into or connected to a grid, a power grid, essentially the grid's an unlimited power source, but the pump is still only going to draw however many watts it takes. So it doesn't hurt the pump at all to have a larger array, and a larger array will produce more power and lower light. So if you need to pump for longer hours in a day, or the weather is hazy or cloudy a lot, using a larger array is a great way to provide more water pumping. So the pump's only going to draw the power it needs, so don't worry about oversizing the array. Other than the cost of the PV array itself, there's really no other effects. So seasonal variation is going to change the amount of pumping capacity, obviously. You're going to have a reduced solar resource at winter solstice than you would in the summer. But typically, in most places, there's greater water requirements in the summer, so that works out just nicely. And you need to size the pump controller or linear current booster to the rated current draw of the pump, not the total array current. So again, if you have a pump that draws, say, 7 amps, you might use a 10 amp LCB. Even if your array could produce 50 amps, that won't matter. There's only going to be 7 amps going through that LCB because that's all the pump is drawing. PV array tracking mounts are another way to get more water from solar pumps from an array. A tracking mount can deliver up to 50% more water delivery in the summertime. It essentially has the same effect as oversizing the array, so you'll have to look at the cost variation between just adding more PV or using a solar tracking mount. If space is limited, a tracking mount could be very cost effective. But these days, with the lower cost of PV modules, it's generally cheaper to just add more PV to the system. So I'm going to go through an example here to give you an example of sizing a system. And in this case, this is a residential water system with gravity flow from the storage tank. Again, if you put a tank up on a hill, you produce pressure from gravity by running that water through a pipe down the hill. It's the same head and pressure calculations that you would use for pumping up the hill. So for instance, if you had a tank that's sitting at 231 feet above your house, you're going to get 100 pounds of pressure at your house, which is more than your fixtures in your house can handle. So you wouldn't want to do that, but that just gives you an example of how much pressure you can get from gravity. So in this case, for this example, we're going to assume that it's a 200-foot deep well with 6-inch casing. The static water level is 100 feet below the ground level, so there's actually 100 feet of water in the well, between the water level and the bottom of the well. We've determined that the well can produce about 20 gallons a minute. In terms of trying to figure out how much water a well can produce, typically when well drillers drill wells, they do an estimate of the water volume the well produces, and they tend to be pretty accurate. Wells also tend to get better over time. As you pump them, you're pumping out and cleaning out the underground passageways that the water is coming in. So typically wells even get better over age. Of course, in areas that are being overpumped, you might have a decreasing water level or decreasing aquifer. So be aware of that. In this case, for this example, we've determined that our minimum daily water requirement in the winter is 1,500 gallons a day, and minimum daily water requirement in summer is 3,000 gallons a day. It's used both for domestic household use and irrigation. There's a storage tank located uphill providing enough water pressure. The water is clean, and the site receives about 3 kilowatt hours or 3 peak sun hours in the winter and 6 peak sun hours in the summer. That's just an example I wrote up here. Actually, here we go. So, you know, the first thing to do, we have a very handy chart in our catalog that we've generated through a computer program supplied by Grundfos. And so using this chart, we first look at the head on the left-hand side, determine that we have 200 feet of head, and then we can move across the chart to see the water volumes in summer and winter expected with different pump models and different number of PV modules. You can see at the top of the chart, we're using 250 watt modules in this example here, anywhere from 2 to 7 in a series string. The SQ Flex pump has a limit of 300 volts DC, so 7 modules in series may exceed that in cold climates, so 6 may be the limit in cold climates, 7 in warmer climates. You can use more modules than that for bigger arrays, but you have to use multiple strings at that point. So for instance, if you needed to use 8 modules, you would use 2 strings of 4, or 10 modules would be 2 strings of 5, or 15 modules would be 3 strings of 5. You know, you just can't exceed the voltage limit for the pump. So in this case, I've circled the model 11 SQF2 pump. With the Grundfos SQ Flex pumps, the first number is roughly the peak gallons per minute that the pump can do under best conditions, and they make a variety of models for that. But we're showing numbers here of roughly 4,200 gallons per day in the summer and 3,000 gallons per day in the winter. However, this is based on Fresno, California, a very sunny spot where there's 7.8 kilowatt hours a day in the summer, and there's 4.7 peak kilowatt hours in the wintertime. So we'll have to adjust that for our site. So in this example, showing 4,237 gallons per day with 7.8 peak sun hours, we need to convert that to 6 peak sun hours for the summer figure. So if you divide the gallons per day by 7.8, you get roughly 543 gallons per peak sun hour. And multiply that 0.6, shows that we have an estimated 3,259 gallons per day in the summertime. There is variation on this, and obviously the strength of the sunlight is going to affect this. High altitude sites are going to do better than this, or sites that may have a lot of humidity in the air, or you're going to get less intense sun, so that's going to affect that. And then we also need to look at our winter usage and do the conversion there. So the winter works out to 641 gallons per peak sun hour times 3 hours is approximately 1,900. So the Model 11 SQF2 looks like it's going to work with 4 PV modules and meet the minimum summer and winter requirements for the site. So a 4-module array will provide sufficient delivery. However, a 5 or 6 module array is certainly going to be more reliable performance. So especially if you have a smaller storage tank, you can't necessarily go for longer periods of time with less sun. I would advise using more modules on there just to make the system more robust and more reliable. Top of pole mounts are generally a good choice for pumping systems. Certainly other mounts can be used. Many times these are used out in open fields. There may be wildlife or livestock. You're going to need to protect the PV modules from cows, for instance. So top of pole mounts are often a good choice. You may need to fence in the PV array if there's a lot of livestock and there's a potential for damage there. You want to place the pump at least 15 to 20 feet above the bottom of the well. As you pump water out of the well, you're going to be drawing in some sediment over time, so you want to have some space under the pump for the sediment to settle without burying the pump in sand or silt. So in this case, with a 200-foot deep well, we really should set the pump at somewhere 170 or 180 feet below the surface to make sure it's not actually at the bottom of the well. And then for this type of pump, you could use 12-gauge pump cable for lengths up to 200 feet with PV arrays of more than 4 modules, because with more than 4 modules in series, you're running a fairly high voltage. So the wire doesn't have to be very big, but 10-gauge wire for deeper wells or for fewer modules where the operating voltage is lower, you want to have less voltage drop in the line, use a bigger wire. In extreme cases, you might even have to use number 8 or even number 6 wire if it's very deep wells and very low power. So be aware of that. And then using a float switch in the storage tank to turn off the pump once the tank is full. And that's used through the Grundfos CU200 control unit and a float switch. And that will turn the pump on or off depending on the depth of the water in the storage tank. So in this example, we're running the 11 SQF2, CU200 controller and float switch, 180 feet of 12-2 wire. Now, if the pump is 180 feet, you're going to actually need some footage above ground to be able to connect up to the CU200 controller. So you might have 190 feet of wire actually to do that. You'll need an underwater splice kit, and that's a kit that has crimps and heat shrink sealants to seal the wire connections. These pumps have 3 wires, so you'll need 3 splices. And then typically a larger piece of heat shrink is used to seal up those 3 seals, provide a secondary seal, and also seal against the pump jacket. And then you'll need a 2-conductor wire for the float switch. That might be hundreds or even thousands of feet long. Excuse me. Grundfos says in their manual that you can go up to 800 feet. I've actually seen situations much longer than that work just fine. It's also possible to do radio controlled switches. That's a whole other setup, but that could certainly be done. In this example, you need somewhere between 4 and 6 standard 60-cell PV modules, all wired in series. Again, if you needed more modules and you can't exceed 6, you would have to use multiple strings. Obviously, you'll need module mounting hardware and a PV cable output long enough to go from the PV array to the CU200 control. They should be fairly close, but in higher voltage systems, the PV array could be even a couple hundred feet away and still provide power to the pump. You just have to make sure you calculate your voltage drop through your wire. You'll need a grounding system. More important for lighting than it is for anything else, since you're not hooked to any kind of grid or anything like that. And then there's an optional controller from Grundfos called the IO101, and that's essentially a transfer switch, so you could use a generator as a backup power source. These pumps are AC and DC. Any voltage between 30 and 300 volts DC or 90 and 240 volts AC will operate the pump. So it can be run off an engine generator if need be, if more water is needed or there's just extended periods of cloudy weather. And the IO101 provide automatic switching between that. And obviously there's other materials you're going to need, just like with any well pumping setup. You need a pump safety rope to hold the pump in the well. You don't want the pump itself to be hanging just on the pipe and the wire. You want to have a cable. Typically polypropylene rope is used, not nylon or polyethylene. Polypropylene doesn't stretch like nylon, and it's rot resistant and sunlight resistant. It's typically what's used for pump ropes. But you could also use stainless steel cables, which are also used. You'll need pipe and plumbing fittings, a well seal, which is what I'm showing in the picture here. It's a cap on the well that seals up the top of the well. You may need perimeter fencing, depending on whether there's wildlife, livestock, or children that you want to protect it from. You'll need a foundation structure for the PV mount. Especially if it's a deep well, you'll probably need a hoist or a crane to lower the pump and piping into the well. If you have some help, you can often do that by hand, but if it's a very deep well, you really need a hoist. And you'll certainly need a hoist to pull a pump out, because at that point, the pipe is generally full of water and is a lot heavier, so you generally need a hoist or a crane to pull a pump out. And you'll need some zip ties to attach the drop cable to the drop pipe. Here's another example here. Filling up a stock tank for cattle. It's a much lower use. Water requirement is only 300 gallons a day in the summer and less in the wintertime. A much shallower well, in this case with a static level of 70 feet. Open pastures, there's excellent sunlight access, and you're filling up a stock tank at the same elevation, so there's no additional head to get up a hill to a storage tank. In this case, a small diaphragm pump such as the Aquatech 4000 would be an excellent choice for something like this, and will deliver plenty of water at that range with just a single module. So it's a much smaller, simpler system. See a diagram of a similar one here. Again, the Aquatech pump, in this case the SWP 4000, and Aquatech has a very nice controller. That's a linear current booster and pump controller. It also operates with a float switch. So you can, that controller is a one-piece power control system. In this case, you only need 100 feet of pump cable, and this pump is only a 2-conductor pump, so you only need 2 wires. Again, same underwater splice kit, and covering for that you'll need, because you have to protect that splice. The pump itself has I think it's a 16-inch lead, but it has wire leads from the pump that you'll have to splice onto in a waterproof fashion. A single module will power this pump quite effectively. 2 modules will power this pump in very low light, so you get a lot more water pumped in a day with 2 modules. Module mounts, PV output cable, safety rope, zip ties, plumbing and pipe fittings. That's what you're going to need for this. And these are very commonly used by ranchers. They're much more inexpensive than the Grundfos pumps. I've even had several ranchers get these setups multiple wells around their property and just, put the well pump down one well and fill up some storage tanks and then move it a few days later to another well and just keep moving it around. They're very lightweight and easy to work with. And that's the pump description. So we have some time here. I can certainly take any questions if there are any. Thanks for attending.
All right, great. Let's get into some questions. We had some really good ones come through. So we'll just pull those up. All right, first question. If you have an elevated storage tank with an inlet near the bottom of the tank, do you have to take into account the weight of any water already in the tank?
That's a good question. It seems like the weight of the water would be a factor, but it actually isn't. It's really the head. So if the tank is, say, 5 feet tall, there's going to be a pressure difference between the bottom of the tank and the top of the tank, for that 5 feet. But the actual weight of the water really has no effect on it. You could have a tank that could be 1,000,000 gallons sitting there, or a tank that's 5 gallons, and it's going to be the same amount of pressure at the bottom of that tank. If you put a pressure gauge on it, I'd say, like I said, let's say it's 5 feet high and it's full, that's going to be what, it's less than 2 pounds of pressure. So whether that tank's 1,000,000 gallons or 5 gallons, it's still 2 pounds of pressure at the bottom of that tank. So it really has no effect. It's counterintuitive, but that's actually how physics works.
All right, great. The next question we have, what is the average PV needed to run a domestic well, 140 feet deep, 1 1/4 casing?
Well, the 1 1/4 casing is going to be your issue there. There aren't any solar pumps that are small enough to fit down there. So unless the water level is very close to the surface of the ground, within 20 feet, it's going to be very hard to pump out of that. There are types of pumps called jet pumps. There aren't any commercially available jet pumps that have DC motors on them. One could certainly be adapted. But jet pumps are horribly inefficient, so it's not really what I'd recommend. There are some pumps available that are essentially designed similar to the type of old-style hand pumps that you would see on a 100-year-old homestead, and those can be motorized. It's essentially similar to what a jack pump would be, and that might be your only option. Other than that, my only recommendation would be to get a well driller out and put a bigger hole in the ground, because 2 inches is just too narrow to get a pump down.
All right, next question. I install DC powered pumps that use a controller. Output is 3-phase wild AC. How does this compare in efficiency to other technologies like Grundfos?
Well, 3-phase pumps are generally very efficient. It just takes a lot more power to run them. I mean, standard AC motors are even being efficient at 3-phase are not nearly as efficient as DC motors are on pumps. So yes, there are certainly pump systems out there that are just using standard submersible well pumps, typically in 3-phase. There are some companies that have some kind of controllers that are able to utilize solar power to run 3-phase AC pumps. They're generally for much larger systems, and there really aren't any off-the-shelf units that are available, at least here in the U.S., to do that. There's some companies that have some proprietary hardware. There's a company called World Water that does big irrigation projects around the world off of solar, and they have a pump controller that they claim can run, if I remember correctly, up to a 300 horsepower well pump. But they don't just sell those parts. They do the service, and they're rather expensive. So there's some companies that are working on the use of variable speed drives to be able to run 3-phase motor pumps directly off solar. But again, there's really nothing on the market at this point in time. You could certainly run a pump like that off an inverter system and a battery. That would be another way to do it.
All right, great. The next question we have, do you provide the design software, and do I contact Grundfos for pump supply?
We would normally love to do that. However, Grundfos recently discontinued and took that program off their website, so it's not really available anymore. They have some new sizing program on their website that I find to be of little use for solar. It doesn't have enough variable inputs in it to really get useful information out. So this is something actually we're struggling with. The program we have is kind of old. It doesn't even have all their pump models on it. So luckily we developed our chart before that became obsolete. I've complained to Grundfos about that, no avail so far. It would be a great project for somebody to come up with that. But unfortunately we do not have that program available for distribution.
Okay, next question. Can submersible pumps run dry?
Generally, no. Submersible pumps are water lubricated and water cooled, so you don't want to run them dry. The Grundfos pump has a little sensor that's installed in the grounding wire, in the wire lead on the pump, and it typically when you put the pump in the well, the sensor hangs about a foot or so above the pump. And if that sensor sees air or sees a lack of water, essentially, it will turn the pump off. I don't recommend using that as a kind of a daily control mechanism. If the well is continually running dry, that's not a great control source because there's only about an inch of water level difference between on and off on the pump. So the pump's going to be constantly going on and off and wear it out pretty quickly. There are third-party control mechanisms that use typically 3 sensors that go at different depths in the well that can control when the pump goes on and off. Unfortunately for DC, there isn't a pre-packaged system for that, but there are several companies out there that provide those kind of devices. But no, you don't want to run it dry.
Thanks, Brian. The next question. Is there a typical pump pipe size?
That really varies. Some of the smaller pumps are only 1/2-inch outlets. Some of the bigger pumps are up to 2-inch. We don't have any pumps greater than 2-inch, but the high volume Grundfos pumps are 2-inch. The low volume ones are 1-inch, and there's a variety of sizes in the middle of that. Many of the Dankoff pumps are very low flow. They may only be 1/2-inch fittings. You really have to check and see what your use is. That doesn't necessarily mean that you want all your piping to be the same size as what the pump is. If you have to run the piping a long way and you want to reduce your friction losses, you could certainly step up to a larger pipe to run the distance. But the actual connection on the pump itself is going to be more size to its volume. So that's anywhere from 1/2-inch to 2-inch for the type of pumps we deal with.
Okay. And have you had any experience pumping sewage from a septic tank? Any recommendations?
Wow. Actually, I have, but not in the solar field. There aren't any, at least I don't know of any, direct PV sewage or sump pumps available. So in that situation, it would be more appropriate just to find an AC pump that's going to do the job, and then you'll have to power the AC pump. That's going to require an inverter to do that, adding an inverter to the system. There are some sump pumps that run off DC. They're designed for houses in case of a power outage. Most of them I've seen are not really high quality. They're typically only meant to be used a few times a year, so they're not exactly long-lasting pumps. But more typically for something like a sewage pump, yeah, you would have to get an AC pump for that and run that off an inverter in your battery system. And then a solar recharged batteries, of course.
Okay. Next question. Do you ever tie a small wind power source in with a solar PV source as well?
That could be done. Grundfos actually makes a controller called the IO102 that was originally designed for a high voltage version of the Whisper wind generators. Well, the company that makes the Whisper wind generators went out of business, so that turbine is not available. But certainly any turbine that can provide power, from 30 to 300 volts DC, or from 90 to 240 volts AC could be used in this situation. And certainly wind power, adding wind to the solar is going to make the system much more robust. In times when there's not enough sun, there may be sufficient wind to do that. It can be done. There just aren't a lot of developed systems for that. It's just too small a market. You could certainly use a wind turbine to help charge batteries to run pumps. I mean, that's a much more developed situation. But if you do have a situation where you really need to use wind, contact me and we can discuss it and see what we can do about that. There's nothing off the shelf right now that I know of, but we may be able to find a turbine that would work.
All right. Next question. What is the duration or life cycle to do a maintenance or change the pump?
Good question. And generally, the more expensive the pump, the longer its lifespan. So for instance, in submersible pumps, like in one of my examples, I had the Aquatech 4000 pump. That's a diaphragm pump and has a brush motor. And what we typically find is about every 2 years, it's a good idea to pull the pump out, replace the diaphragm and the valves. There's some spring-loaded valves in there. And typically the motor brushes, or at least they should be checked about every 2 years. It depends on the cycle. I've seen them last for 5 years easily. But if you don't perform that service, what happens over time is the diaphragm tends to get stiff and it may split, and that will flood the pump motor with water and generally ruin the pump. So it's a good idea to have to pull them out and service them. Pumps such as the Grundfos SQ Flex is all stainless steel, brushless motor, very few wearing parts, and they generally have a lifespan of 15 to 20 years, just like a standard well pump would. And I've even seen them last longer.
Thanks, Brian. The next question we have, will the check valve prevent back pressure on the pump drop line or the run from?
Yeah. Typically, submersible pumps have a check valve built into the top of them. If they don't, one should be added. And yeah, a check valve is a very good idea. It just prevents the piping system from draining back into the well, and essentially you've lost a certain amount of water that you've used energy to pump. It's not urgent that you do that, but yeah, it's usually a good idea to keep the water in the pipe. The one difference there is if you have freezing issues, and I didn't really go into that in the presentation, but if you have situations where the pipe may become frozen, you need to take action for that, either burying the pipe or having some way of draining the pipe back into the well so it doesn't freeze once you stop pumping. There's a variety of ways to do that. The simplest is to drill a pinhole in the pipe just under the well cap near the top of the pump. And yeah, while it's pumping, a certain amount of water will be lost out of that weep hole, but then when the pump shuts off, water can drain out of the pipe back in. There's a variety of other ways to do that, but any local well driller or well pump person that's familiar with pumps in your area will know of all the strategies that you need to keep the pipes from freezing. And essentially a solar pump is no different from a regular pump at that point.
All right. The next question we have, if the water source provides a very dirty water with lots of sediments, how can you filter it before it enters the pump? What would be the bottom hole well assembly?
The bottom hole, that's hard. There's a couple of companies. One is called Lakos. They're the most common ones. They make a sleeve that goes over submersible pumps that causes the water being drawn into the pump to be kind of spun on the outside of the pump, which spins out the heavier particles, which can then settle into the well. They're considered sand filters. They don't necessarily work with very fine silt, but generally the pumps can handle that, so that's usually not a problem. It's more for sand. So there are sand filtration devices out there for normal submersible well pumps. Again, not something we carry, but they are available out there, and it would work just as well with, say, a Grundfos pump as it would with any other AC pump. So if you do have a lot of sand in your well, I would certainly look into doing that. It's going to greatly reduce the wear and tear on the pump.
Great. And we'll move on to our final question here. When do you typically need to use a linear current booster with your pump to get started?
Most of these pumps require a linear current booster. The only ones that really don't are some of the centrifugal pumps, like for instance the Dankoff Suncentric. Because of the centrifugal nature of it, it's only a single impeller pump. That impeller can spin in the water with very little resistance. It's not actually pushing the water until it gets enough RPM. So the motor, with very little light, will start to turn. All these other pumps, especially the positive displacement ones, are essentially trying to turn under pressure. They're trying to pump water even with 1 RPM, and that'll stall the pump until there's sufficient amperage from the PV array to get it going. So what you end up with is a stalled motor with current flowing through the brushes, and that can overheat the brushes and the commutator. So what the linear current booster does is it takes the voltage, because the PV module produces pretty good voltage and very low light, but very low amperage. But it kind of similar to MPPT, to where it takes that additional voltage and convert it into more charging amperage. So it might go down to even 5 volts DC, but boost the amperage enough to actually get the motor spinning. It won't necessarily be pumping water at that point, but at least the motor is turning until the sun rises more, for instance, and you get more power, and then you get more RPM, and the voltage will climb at that point. So almost all of these pumps require an LCB of some sort. The Grundfos SQ Flex, it's all built into the motor, so there's no additional separate pieces for that, but most of the other pumps do require a separate LCB.
All right. Well, thank you so much, Brian. That concludes the Q&A portion of the webinar. Thank you, everyone who submitted questions. And for those of you that we couldn't quite get to your question, I'll send them over to Brian, and he can do his best to answer them for you. Thanks again for joining us for the presentation.
Thanks, anyone. And, of course, you can contact me directly with your pumping situations. I'd be glad to help.